All right, let's continue. So we covered these three topics so far. Now we're going to talk about support vector classifier and polynomial feature expansion. So with support vector classifier, we're going to consider a soft margin. And as you would expect, there are some benefits to a soft margin. For example, if the data is noisy, we can still get the classifier, and it's not going to have non-robust behavior. And also for the cases where the data is not separable, again we're going to have a solution. So support vector classifier. Let's consider this data set that has a bit of overlap. So it's not linearly separable. Yeah, something like this. So we have x1 and x2. The type of these points represent the classes. So let's say x is tuna, O is salmon. And again for this one, let's say y equals -1. For this one, y equals +1. So with the idea of a soft margin, we're allowing some points to be on the wrong side. So of course there is no way that we can find one line that separates this. This is because even if we try to pass a line here, it's going to, let's say, go like this. So the data set is not linearly separable. Of course, with a nonlinear boundary, we can separate this, right? But this is just an illustrative example. In reality, we use SVM for much more complicated problems than this. So with a soft margin, the idea is that we allow some of these points to be on the wrong side. So we can get this hyperplane with a soft margin, and the margin would be something like this. And same distance here. So just for the sake of illustrating a point later on, I'm going to also make the problem a bit more nonlinear. So even if we have even if we have an x here, O here, we can have a soft margin like this. For this soft margin, it's essentially classifying this part of the training data set correctly and this part of the training data set correctly, but there are some points that are on the wrong side. For example, this one is on the wrong side. This one is also on the wrong side, and these 2 points are also on the wrong side. And then there's this point that is based on the decision rule, based on the hyperplane. It's on the correct side, but it's on the wrong side of its own margin. So the margin for class O is actually this one, and this is on the wrong side of its margin. This one is on the wrong side of its margin, and this one is on its margin. Let's say this x is also on its margin. So later we're going to have a special name for these observations. These are actually the observations that define the orientation of the hyperplane. And they are the essentially main observations that define this boundary, define this classification rule. So after finding them, we can get rid of the rest of the data. But the thing is, we need all the data in order to find these important observations. So, but how does the optimization work? So it's a similar optimization problem. We want to maximize over these betas. But now we're considering some slack for every single observation. So the constraints are as before, from 1 to p, sum of beta j squared is 1. And for the second constraint, I think we had something like this: yi times f of xi should be larger than m. Now we're considering a slack of 1 minus epsilon I for all observations. So these slack variables are non-negative, and there's a total budget of C, capital C, for these slack variables. This budget defines the width of the soft margin. So if we have more budget, we can actually have wider, margins. And when budget is 0, we go back to the previous case where we had a hard margin. So with SVC, it also works on non-separable data, and it has a soft margin, so it is not fitting hard to the data. It has a hyperparameter C that kind of controls the complexity. So we can tune this hyperparameter by cross-validation. And we get, essentially a model that is flexible, and because of its flexibility, we want to make sure that its level of flexibility is suitable for the level of complexity in our data. If our data is like this, you can see it's, just a bit nonlinear, right? So then a margin like this is sufficient. But if there's a huge overlap between the two classes, probably the suitable value of C would be a higher value, and the margin should be a bit larger. And everything that we see in here is just training data. We still don't know how these models are going to perform on test data, which is what we actually care about. So with this example, we had 1, 2, 3, and 4. Four observations on the wrong side. And we had 1, 2, 3. 3 observations on the wrong side of their margin. So there are 7 points that seem to be kind of special. We're going to come back to them later on. So the thing is, even with the soft margin, we made some improvements, but with the soft margin, we cannot properly classify, a data set like this. So if we have a data set that is, somewhat, separated, so there's some, distance between these, groups, but the boundary that kind of separates this, the boundary is nonlinear. So, if our data is positioned like this, if you're talking about 2 types of fish, where one of them is, somewhat in the middle in terms of weight and length, and the other type of fish has like the small version and large version, right? So, and it's either, short and light, or long and heavy, then we cannot classify this, even with a support vector classifier. So the soft margin kind of brought us some benefits, but there are still some challenges that we cannot solve, because if we fit SVC on this data, I guess it's going to maybe do something like this, which is not helpful at all. So even a soft margin fails on this non-linearly separable data. So this is not just a matter of whether data is separable or not. Here, there is some gap, but we need a hyperplane that kind of does something here and then also makes some distinction here. And it wouldn't be just one straight line in 2 dimensions. So what we need is a method for introducing some nonlinearity to this idea of finding a hyperplane. So far our hyperplane was just a linear combination of these betas. So it has, if we had p dimensions, our hyperplane, was a subspace with d-1 dimensions, right? For example, in 2D it was a line. In 3D it would be a flat surface. Now we want to introduce some nonlinearity to this. So, any questions so far? Yeah. Yeah. Epsilon, we have epsilon for every data point. For example, let's say for all of these points in here, epsilon is 0. For all of these points in here, also epsilon is 0. but for these 7 special points, epsilon is the difference between is the difference from here to here. So this is epsilon. Also, this is epsilon here. This is epsilon here. And yeah. So for these 4 observations that are on the wrong side of the hyperplane, there is some non-zero epsilon values. Yeah.
I guess that maybe it's from the other like, isn't epsilon, if you classify it in the wrong side, epsilon should be greater than 1.
So when epsilon is 0, we get something similar to the previous problem, because this thing becomes m. And when epsilon is non-zero, here instead of m, we have, let's say, something like 0.95 m. So we're giving some slack to this requirement.
Yeah, but when you classify it in the wrong side, the side will be reversed. So you will got a negative result. For example, classify it as channel and
oh yeah, that's right. So then in that case, function f.
So also you will have an epsilon greater than 1, so you will get a...
Yeah, greater than 1. Well, I can double check the course textbook, but no, epsilon is greater than 0. So yeah, I didn't explain exactly what is the f function in here, so I think that's where the answer is. So I can hopefully answer you later. So I need to check what is the f function in here. I assume there is some epsilon in it that takes care of these cases which are on the wrong side, because we are tolerant of some cases being on the wrong side, but we just have a total budget for this tolerance. All right, so even a soft margin will not be able to resolve this issue of non-linearly separable data. So the next thing we're going to do is trying polynomial feature expansion. So with polynomial feature expansion, the idea is that, let's say here we only have x1. If we only have x1, same data only with x1 would look like this. So they should be exactly on the line, but just to illustrate, adding some noise to them. So these are the same thing. And there were like some circles. Right? This is one dimension. These must overlap, right? So this is not linearly separable. But quite magically, if we expand the feature space, so this is one dimension, and move to 2 dimensions, this becomes linearly separable. So to me, this is the most exciting feature of separating hyperplanes. So here, if we keep x1, but also include x1 squared, what's going to happen? Well, x1 squared would have a pattern like this, right? So these circles end up here. And then these x's end up here. And then these o's end up here. So we expanded the feature space from 1D to 2 dimensions. So these are the circles. Now in this expanded feature space, the data is linearly separable. So this is the magic of separating hyperplanes. This is meant to be a straight line. So if I drew it properly, I think you can imagine that because of this curvature, suddenly the data that is non-linearly separable in 1D becomes linearly separable in 2D. So the idea was that I just added one additional column. In the original data, we had x1 and x2, so the original feature space was 2D, but essentially what I did here was including some additional feature. So, for example, in this case, if our original features are x1 and x2, we can use polynomial feature expansion, so our data looks like this. We have x1, x2, and y. I'm going to expand the features and include something like x1 squared. I'm going to include something like x1 times x2. So let's say if from 2 dimensions, I move to 9 dimensions and include all of these. So I keep x1 and x2, but also include x1 squared, x2 squared, and x1, x2, also they're cubic terms. So x1 squared, x2, x2 squared, x1, x1 cubed, and x2 cubed. So in here we have a total of 9 dimensions. These are just expanded features. So this is just weight of the fish squared. This is weight times length of the fish. So creating these additional columns should be pretty easy. Then we move from 2 dimensions to 9 dimensions, and then this nonlinearly separable data becomes linearly separable in 9 dimensions. So we find the hyperplane in 9 dimensions using, using a support vector classifier. We find it in that high dimensional space, and then when we project that linear boundary from 9 dimensions back to 2 dimensions, this would be the result. We get a boundary with a soft margin here, which is also has some curvature, possibly. If we need it, it has the flexibility to bend a bit. So, what are these surfaces? These are nonlinear decision boundary in 2D. Where we got them from? We got them from using a support vector classifier in 9 dimensions. In 9 dimensions, this thing is just a surface. It's just a flat, let's say, flat affine surface in 9 dimensions. But when we project it back to 2D, it becomes something nonlinear. Yeah.
So you think project back to 2D is just like a transformation?
Yeah, it's a transformation that allows us to reduce the features. So, for example, when you multiply some shape to a matrix, if the shape is 2D and the matrix is 2 by 3, the result is going to be a 3D shape. So similar to that, with some matrix operations, essentially, we move back from 9D back to 2D. And then we get some, rotated and kind of transformed shape, which looks like this in 2D. And the idea is that we somewhat circumvented the nonlinearity, because this was nonlinear. We moved to 9 dimensions where the complexity of the problem is nothing for that 9 dimension. In that 9 dimension, the problem suddenly becomes a simple problem. So if we solve it, we find that separating hyperplane in 9 dimensions. When we have it, then we project everything back to 2 dimensions and we get something like this. And the software takes care of all of this for us. This is just what happens under the hood. Yeah. Well, we had feature expansion here. This is what we need to do if we want to kind of code it ourselves. But essentially, when we do this polynomial expansion and then fit a SVC on it, then we get a suitable boundary, because the boundary would look like this for the original data. We cannot plot it. I mean, this is the projection of that line, of that surface. So maybe, just to give you an idea of what's going on, let's say if we have, if we have a 2D shape like this shape is only a collection of points. When we project it into 1 dimension, when we essentially collapse it into 1 dimension, it becomes a line like this. What is this line? Is the projection of this point onto this subspace. Projection of this point here. So when all of these are projected, this is orthogonal projection. So each of these is going to have some shadow on this line. When we take the collection of these shadows, it would be a straight line. But the software takes care of all of this for us. So here, the main thing we needed to do was doing the polynomial feature expansion. And the idea is very simple. We had x1 and x2. So if you are willing to include up to cubic terms, we can have all these additional features. Later on, we're going to see how we can actually automate this part as well. So we want the support vector machine to actually do this expansion as well. So then it becomes even more, I think, useful for applications. Any questions? All right. So for seeing how we can automate this, so I covered this. For seeing how we can automate this, feature expansion, we need to first talk about inner product. So this part is a bit theoretical, but we need it for understanding how kernels do that feature expansion for us automatically. So inner product in SVC. So the thing is, in SVC, we had this function, right? Which was beta 0 plus xj. So xj is, feature number j times beta j from 1 to p. There is another representation of the same hyperplane, and that representation involves inner product. So it would be something like this. it's beta 0 plus another sum. This time the sum is from 1 to n. And we have some weights like alpha sub I times inner product of x and x star. So the inner product, just to recap, if you have two vectors, this is some vector x1. So these are vectors. If you have a vector this and another vector like this, the inner product of this, we can represent it like this, and the inner product is just the sum of multiplying, the corresponding entries. So 1 to 3, 3 plus 2 times 4, 8. So this is inner product. So inner product is somewhat related to the similarities between vectors. Because if two vectors are orthogonal, their inner product is 0. Sorry? Projection. Yeah, we can also think of it as some sort of projection, yeah. But I think for this representation, it's more useful to think of them as similarity between two vectors. Because when two vectors are pretty much have the same direction, their inner product is going to be larger, right? The inner product will be almost close to norm of this times norm of this. Well, if two vectors are exactly in the same direction, so 1, 1, and 2, 2, the inner product will be 4, right? Yeah. So it's as large as it gets, right? So then for these two, it would be a bit smaller because they have some dissimilarity, and then when two vectors are orthogonal, their inner product is just 0, like 0 and 1, and 1 and 0. These are two vectors that are orthogonal, and their inner product is 0, right? So that's why we can think of inner product as some representation of similarity. So this is the model, but then for finding these coefficients, which are to be estimated, we need all, let's say, inner products. Actually, it's all n choose 2 between pairs of observations. So if in our data set, if this is represented as vector x1 and the second row is vector x2, in order to be able to find these alphas for this second representation of the hyperplane, we need this inner product, as well as x1 and x3, as well as x1 and x4. In total, there are n choose 2 pairs of observation. We need the inner product of each of them. Each pair of them, essentially. So if you want to use this idea of this representation, it involves a lot of calculations, because when n is large, this thing is also large. This is like n squared, right? This grows with n squared. But then kernels handle the calculation of inner products. So kernel is a function. For example, we have polynomial kernel, we have radial kernel. So with the polynomial kernel, we're trying to get the support vector machine that comes from the feature expansion to this polynomial expansion. So if we use that polynomial kernel, which is just some function, this part of the process will be automated for us. Yeah.
Why do we want to change the function from that to that form?
Because here, this is the best that we had before introducing the idea of automating the process. So as long as you're happy to do this feature expansion yourself, you don't need that. But then, if you want the machine to take care of this part for us, you need to talk to the machine in their language. And apparently, this is the language of the machine. So the thing is, after estimating these, actually, most of these alphas will be 0. So most alpha i's are 0. Therefore, f of x can be represented as beta 0 plus I from S. S is a support set of alpha I times x and x star. So S is a support set, which means the set of indices for which alpha I is not 0. So now back to the previous story. What are these indices? These are the indices. The support set for this example has 7 index in it. The index of this observation is in that set. Therefore, its alpha would not be 0. The index of this is in that set. Index of this, and this. So in this example, size of S is going to be 7, which is 4 plus 3. So the observations which were either on the wrong side of the hyperplane or on the wrong side of their margin or on their margin, they're going to have non-zero alpha values, and they are the observations that define the orientation of the hyperplane. Because eventually what matters is this hyperplane, and we didn't want the orientation to depend on one single observation. We didn't want this model to be affected by one observation here. So with the hard margin, we noticed that as soon as we introduce one observation here, the hyperplane will be tilted like this, which is some non-robust behavior, which we didn't want. Now that we're considering a soft margin, if we add additional training data point and it ends up here, it's going to have no impact on the hyperplane or the margin. If we add additional data point and it's somewhere in the overlapping region, so if it ends up here, it is going to have some impact, but that impact is moderated because of these other 7 support vectors. So the behavior, I mean, the hyperplane changes, but the change would not be such, dramatic. Which is what we want. We don't want the hyperplane to be totally different from the new version of the dataset. So xi, such that I belongs to S, are support vectors. So that's just a name that we have for these, observations that define the orientation of the hyperplane for us. So in a sense, with this method, we are also achieving some sort of sparsity. Because if you remember from lasso and ridge regression, we had sparsity in the sense that most features did not matter in lasso regression. Or in ridge regression, they get really small coefficients when we have regularized fitting, and that is called sparsity. In here, we have another sparsity, but the sparsity is between observations. As you can see, most of the observations are not going to end up being support vectors. Only a relatively small number of observations are going to be support vectors, and therefore only a relatively small number of observations define this hyperplane eventually. So in a sense, we're getting some sort of sparsity, which is what we need for working with classification in high dimensions. Yeah.
So in the actual calculating the hyperparameter process, we are first taking in some data point, and then we iteratively update the hyperplane, and some of the data will be removed from the set.
So if you're talking about the maximal margin classifier, for maximal margin classifier, we just solve. For maximal margin classifier, we solve this. Either there's a solution or there's no solution. That's it. So there's no iterative process. Then the details of how we solve this optimization problem, that's not really, we're not really concerned about that. Then for maximal margin classifier, we solve this problem, and we get the optimal values of beta 0, beta 1, all the way to these slack variables, and that would be the maximal margin classifier. That would be support vector classifier without kernels and without feature expansion. Yeah. Now with support vector machines, almost always we have some kernels. The kernel is some function that is replaced here instead of these inner products, because the value of that kernel function is going to be equal to the sum in here, and it doesn't really, it essentially finds the value of that sum without actually doing all all these inner product calculations. So an example of a polynomial kernel is this. So polynomial kernel is what allows us to do polynomial feature expansion automatically. The function that we get when we use polynomial kernel is beta 0 plus alpha I, some function k of x and x star. So when you use the software and you want to use support vector machines, you can choose whether you want polynomial kernel or a different type of kernel. Another type is RBF. RBF or radial basis function or just radial kernel. It has a different formula. The formula has something to do with the multivariate Gaussian distribution, but you don't need to worry about the formula. It's a bit complicated, but it is some function that we use in here, and it allows us to actually do feature expansion by going to some infinitely dimensional space. So as this is now getting very complicated, let's take another break and then we discuss this magical thing. But any questions? Yeah? So here, alpha I are the weights that we have in the representation of hyperplane based on observations. So this hyperplane, you either define it based on features, which is very straightforward and easy to understand, but the same hyperplane is also representable in the sample space, in the space of observations. There are n observations, and that hyperplane can be also represented in that subspace, in that space. Potentially, yes, but actually, no. Potentially, we have the flexibility to have all these alpha i's being, being non-zero, but most of them end up being zero. Yeah.
So we end up with a new dimension that is less than the number of samples but greater than the number of samples.
Yeah. So here, this polynomial kernel has some hyperparameter. I forgot this part. It has some hyperparameter d, and these nine dimensions that we got in here was because we included up to cubic terms. So in here, small letter d is actually 3 because we did up to cubic expansion. And then with this polynomial kernel, it's up to us how much we expand the feature space. If we use d equal to 3, and originally we have 2 features, that essentially takes us to some 9-dimensional subspace, sorry, 9-dimensional space where the features are these. So, I mean, in that, if you're using the kernel, we don't even use this representation. We use this representation, and then what matters in here is not features anymore. It's not the number of features or dimensions. What matters is actually S, which is the number of support vectors. So I can tell you exactly what that is. So we expanded to 9, and let's see. This one is on the wrong side of its margin, that's 1. This one is on the wrong side of its margin, that's 2. Let's say this one is on the margin, that's 3. Then these 3 are also on the wrong side of their margin, so 6. So what matters here is that after feature expansion to 9 dimensions, S, the support set is going to have 6 observations in it. Essentially, the orientation of these lines are defined by these 6 observations. Normally, there should be also something here. So it's, for my example, it was a bit unusual. There must be also something here to define this margin. But yeah, after we use polynomial expansion, then the problem is not about features anymore, but it is about support vectors. And in this example, let's say we had 6 support vectors, because there were 6 points on the wrong side of the decision boundary, or on the wrong side of their margin, or on their margin. Yeah.
So how does change like a hyperparameter dimension affect the number of features when you're using the kernel method? How does that affect? I can say if you change the hyperparameter dimension to 1 to 3, like how does that affect the number of features when you're using the first, I don't know how does
Yeah.
that change hyperparameter, like when we're using the kernel.
Oh, the hyperparameter. So in polynomial kernel, there is some hyperparameter. When we want to choose polynomial kernel, the software also asks us for some value for the hyperparameter.
So it has been taken into K.
So this is, if it is 3, it means that we want up to cubic feature expansion. If it is 2, it means we want up to quadratic feature expansion. And then quadratic and cubic, the number of features, expanded features we're going to have also depends on the original number of features. For example, if the original number of features is 2, x1 and x2, then cubic becomes 9. Because these also depend on x1 and x2. If I had x3, the cubic expansion would have been more than 9 features, right?
So what's X star? X star is a
X star is, sorry, I mean, this should have been xi. So most of the questions I get from you are because I'm using wrong notation. So this is over I, so this is xi.
So if we want to make sure about S, so we can do this one first. Let's calculate the number of, like the number of observation on the one side of Hyperplane, right?
Sorry, I mean, we don't control that.
I just mean, if we want to know the S, right?
Yeah, we know S after fitting the model.
Okay.
Yeah.
So, and how we calculate alpha I?
Alpha I?
How we calculate alpha I?
Alpha I comes from, alpha I is actually how the model is fit. So, yeah. So,
What's the range of alpha?
so it's like betas pretty much. So these are some coefficients. Yeah. So these are not about slacks anymore. This is something else. So when we fit the model, then this is essentially the impact of each of those support vectors to the hyperplane. They don't have the same impact.
So in the computer, like if we want to copy this one, we can do this first and then do this one.
So when we're using a support vector machine, well, we choose the classifier and then we choose the kernel and we fit it. Then usually we need some cross-validation, maybe for this. And if we use RBF, which is the more popular kernel, there is another hyperparameter to be tuned. So actually using support vector machine is much, much simpler than what we are talking about today. So using it is pretty much calling the library, right? Calling some function to fit a support vector machine with, let's say, RBF kernel, and then doing the parameter tuning with cross-validation. That's it.
How we choose the kernel?
Sorry?
How we choose the
Kernel, depending on the nonlinearity that we expect in our data. So this RBF is, so useful that pretty much this is the go-to method. Yeah, I haven't really discussed it yet, but it's very magical. So when we have access to RBF and polynomial kernel, I would first try this and see how good the model is on some test data. And if it is good enough, I stop right there. Yeah. So using SVM with RBF kernel is I think, the natural thing to do when you know that there's some nonlinearity in the data. Other questions? All right, let's take another quick break, and then we discuss radial kernels, and then comparison to logistic and LDA, and also multi-class classification.